All right, so let's try graphing um, some cosecant and secant given the equations. All right, my opinion, my personal opinion, graphing cosecant and secant, and I feel this way about tangent and cotangent, is a little bit easier than graphing sine and cosine. The reason is because with sine and cosine, you've really got to be really careful about the phase shift. Um, with secant and cosecant, though, because they have asymptotes built into the mother functions, it makes it a little bit easier. So just as a reminder, here's like this top one is cosecant. So these dashed lines, those are asymptotes. So the way that I go about graphing cosecant and secant by hand is by first finding the asymptotes, laying out the asymptotes. And then from there, I essentially just use some symmetry that I'll talk about, some symmetry that happens between the asymptotes to basically just give me an idea of what the graph will look like. So let's do that. Right, so the first thing that I want to do, this equation is a cosecant equation, so it's y equals 2 cosecant 3x minus pi plus 1. So it's got everything built in there. It's got some change in amplitude, which we'll talk about what that means for these functions. It's got some change of period. It's got a phase shift, and it's also got a vertical shift. It has everything in there. So the first thing that I do, I guess maybe what I should do first, just because I know this can be really common, and even though I said just now that I don't really personally pay too much when I'm graphing these, I don't pay very much attention to the phase shift, you might still be asked. It's still really common in these kinds of questions to be asked, what is the phase shift? Fortunately, it's the exact same thing as what happens with everything, sine, cosine, tangent, cotangent. So the phase shift of this occurs in here. And in order to find the phase shift, you've got to divide out this B piece. So for me, it's a 3. And what I mean by that is you might, if this is helpful, it's pretty easy. You can probably just do this in your head. But if it's helpful to maybe see it like symbolically, you might rewrite this as 2 times the cosecant of, and then I'll do a square bracket, and I'm going to, from 3x minus pi, I'm going to factor out 3. I'm going to divide out that 3. So 3 times, parentheses, x minus pi over 3. So I'm pulling that 3 out of everything. 3x divided by 3, pi divided by 3 gives me x minus pi over 3, plus 1. And once you have your function in this form, this piece right here directly tells you what the phase shift is. So if you were asked what is the phase shift of this function, it is pi over 3 units. And of course you need to specify is that to the left or to the right. Since this is a minus sign, it's kind of like the counterintuitive thing. Since this is a minus sign, this is a shift to the right. So this is pi over 3 units to the right for the phase shift. What else might you be asked? Right, period, and this actually is, period is something that I use when I'm graphing this thing. So the period, exact same thing, 2 pi over b. So for secant and cosecant, it's 2 pi, technically 2 pi over the absolute value of b. In this case, b is positive anyway, so it's just 2 pi over b. So 2 pi over 3 is the period. You might be asked what the amplitude is, and it's still just given to you the same way. I might be using amplitude sort of incorrectly here, but it does still have, like, unlike with tangent and cotangent, where it was like, no, amplitude literally doesn't make any sense. It's just kind of like a stretch, vertical stretch or shrink factor. On the one hand, the amplitude does affect that vertical stretch or shrink, but it also affects the distance that, like, So secant and cosecant, these are like they're like U's. That's how I view these, like little U's here. So amplitude does affect the distance from the midline to the vertices of the U's. So it both kind of like stretches the U, and it also affects where that vertex is. So if you were asked that, the amplitude here is 2. Okay. So as far as graphing, right, and I guess you might be asked, like, what is the midline? So the midline is, for this one, y equals 1. The vertices for these functions would be midline plus or minus the absolute value of a, and that gives you the range. So I'm just kind of like listing all of this out. Again, like I don't use all of this when I'm graphing. I just mentioned a second ago that I use two things. I find the asymptotes and then I use the period. And then I use the symmetry that's built into these. But I can see where these things might be asked of you. And sort of you might be asked to, God, I spit. You might be asked to specify some of these without graphing it. So the vertices are of the U's, they are going to be at, sort of generically, they are at D plus or minus the absolute value of A. So in this case, they would be at 1 plus 2. So I guess it might be kind of a weird way to write this, but the vertices would be at y equals 3, at least for the y value of the vertices, it's at y equals 3. And also at 1 minus 2, negative 1. So that's where the vertices would be, which then also from that gives you the range, which would mean that the range is everything from negative infinity, because these things stretch off in both directions towards negative infinity and positive infinity. So the range would be negative infinity to negative 1 and 3 to infinity. Oops, and these should be square brackets because they actually hit these values. My mistake. Square brackets. There we go. So that's the range. If you're asked that, me personally, I tend to not ask that. I'm a little bit more interested in, can you just graph the thing? Because if you can graph it, the vertices and the range, all of that is just kind of apparent. All right. So let's see here. The first thing that I do is I'm going to figure out where is exactly one asymptote. I only need to find one. I don't need an expression unless you're asked for it. I don't need an expression that gives me every single asymptote. Okay, so I'm just going to find one. Cosecant is the reciprocal of sine, which means that cosecant theta has asymptotes wherever sine theta is equal to 0. And this piece right here, you can think of this as theta. All of this whole piece, 3x minus pi, is theta. So we want to find where does 3x minus pi, or theta, equal 0. And that's a nice easy one to solve. It's when x is pi over 3. So I know that there is going to be an asymptote at pi over 3. I have the period as well, which means that every 2 pi over 3 units away from pi over 3, there will be another asymptote. And that's only kind of half the story when it comes to the asymptotes. I'll show you why. Let me start graphing this thing first so we can start putting some of this together. There we go. All right, so I know that there is one asymptote at pi over 3. Period is 2 pi over 3, so makes a lot of sense that I would make my units here as pi over 3 units. So I'll say here's pi over 3, 2 pi over 3, 3 pi over 3, or pi. And going in the other direction too, negative pi over 3, negative 2 pi over 3, negative pi. All right, so I'll put in at least where I know that there are asymptotes right now. I'm just trying to make this thing piece by piece. I'm just kind of bringing it together. And that's definitely how, unless you are like the Rain Man type, that's how you should be thinking about this, just piece by piece. Find one piece and okay, one piece of the puzzle rather than like trying to put all of it together at once. All right, so I said that plotting these asymptotes so far is only half of the story. And the reason is because with cosecant, one period, one full period, and the same with secant, one full period is two of these u's. So this graph right here, this is two periods. Here's one period, here's the second period. Notice that within one period, there are actually 1, 2, 3 asymptotes. That is to say, within one period of the function, there's an asymptote going right through the middle, cutting right through the middle. So this is one period of the function because this is an interval of 2 pi over 3. This is one period of the function, which means that this interval is also being cut exactly in half by another asymptote right here at 2 pi over 3. All right, so now I've got at least like one full period here that I'm kind of listing out. I know that there's going to be u's in these intervals somewhere, but I don't know where. Well, I guess I do know now where the vertices of the u's will be. And I could probably just sort of like logic my way through where like for instance, does this sort of slice of the period, does it have an upwards facing u or does it have a downwards facing u? So that's the very last thing that I need to solve for. And I only need to solve it once because these things alternate. So once I've solved it once, I'm good to go. And the way that I solve this personally, what I like to do, once again, looking at these graphs, so if you look in sort of 1/2 period, just one segment of these u's, the vertex of that u is at exactly the midpoint between the two asymptotes. So what personally I like to do, and maybe your teacher will allow you to do this, rather than thinking about like the phase shift and all that sort of stuff to try to find points, is just plug in a midpoint. So for instance, so this is pi over 3, this is 2 pi over 3. What is the midpoint between pi over 3 and 2 pi over 3? Well, add these together and divide by 2. It's pi over 2. So exactly right here is pi over 2. I know that's small. So pi over 2. And I know that there is going to be some vertex of a u here at pi over 2. Well, which of the vertices is it? Is it the one that's at 3 or is it the one that's at -1? I don't know. Me personally, I'm just going to plug in x equals pi over 2 and see what comes out, and it'll tell me. So when x is equal to pi over 2, I have 2 times the cosecant of what ends up being 3 pi over 2 minus pi plus 1, which is 2 times the cosecant of 3 pi over 2 minus pi is just pi over 2 plus 1. Cosecant of pi over 2, well, sine of pi over 2 is 1, which means that the cosecant of pi over 2 is 1. So this just becomes 1. 2 plus 1 is 3. So this is telling me that when x equals pi over 2 in my function, y equals 3. So let's see here. I'll go 1, 2, 3. At pi over 2, it's at 3. The very last thing is, and this might already be obvious to you, you might be wondering, is, well, okay, we found this vertex, but is the u facing up or is it facing down? These u's never cross the midline. So since this is above the midline, it's upward facing. I guess you could also sort of deduce that from the range, that there's nothing between -1 and 3. That's not part of the range, so this must be upward facing. And because this has this 2 out front, I might make my u just kind of like steep, something like this, just to kind of represent that it has undergone sort of like a stretch, this stretching, vertical stretch factor. So there's one part of it. All right, nice and easy though, graphing the rest of this, because I know that the next part, this next segment, this next slice is going to have a downward facing U. I know that the downward facing U has a vertex at -1. And it's going to occur right at the midpoint between these asymptotes. So it's going to be right here. Same thing, just to the best of my ability, try to make this look a little steeper. There's one period. If you needed to draw 2 periods, it's just the patterns. At this point, you shouldn't even need to like really think too hard about it. It's going to be right here, and there'll be one right here. Be an asymptote here. I just put the asymptotes on there because it helps me to make my graphs a little, man, that's an awful U. Make my graphs a little bit more precise. Okay, so there are 2 periods of that graph. Let's try another one. And this time around, I'm just going to jump straight into graphing it. I'm going to write out a couple of these pieces, but I'm not going to write out all of them. So let's see here. Which pieces do I want? On the one hand, one thing that I will write out, even though I don't use it, is the phase shift. And I'm going to write that out because I think it's really common for people to make a mistake when they're asked what the phase shift is. So the equation is -1/4 secant 2x plus pi over 2 minus 2. So what is the phase shift of this thing? You may need to convince yourself of this, but it is pi over 4 to the left. Remember, you've got to factor out b. You have to factor out this 2 to get the phase shift. So when you factor out the 2, you get pi over 4, and it's moving to the left. Period is 2 pi over b, so 2 pi over 2, or pi. Right, and maybe I'll just specify the midline. That is kind of helpful. Midline is y equals -2. Yeah, that seems good. All right, an asymptote. Let's find an asymptote. Well, secant is the reciprocal of cosine. So we're looking for where does cosine of theta equal 0. Cosine of theta equals 0 at pi over 2. So I'm solving where does 2x plus pi over 2, or theta, where does theta equal pi over 2, which is where, because cosine of pi over 2 is 0. That's all I'm solving for. So solve this out. Let's see. I subtract this from both sides, and I get 0. So yeah, this is x equals 0. So there's an asymptote at x equals 0, or the y-axis. All right, and just kind of like thinking ahead for making my graph, the midline is at -2. The amplitude, or the distance from the midline to the vertices, is a distance of 1/4. So there are going to be vertices at -1.75 and -2.25. So most of this graph, the kind of the meat of this graph, is occurring below the x-axis. So I just say that because like this top graph, you know, I pretty much centered the origin. This time the origin, I'm going to move it up a little bit. Maybe, yeah, this should be good. I don't know. Let's try it. Right there. And yeah, something like that. That seems good. All right, well, on the one hand, I guess I didn't need to move the ruler because I know that there's an asymptote that goes through this thing. And even though it's going through the x-axis, the y-axis, I'm still going to put the dotted line there, just as like a visual cue for me. One period away from this asymptote will be another asymptote. So I'll kind of want to mark this off by units of pi over 2, remember, because we need to split each of our periods in half. So this is pi, and I'll go in the negative direction too. -pi. So I know there will be an asymptote here at pi. And because these asymptotes are all split in half, each period is split in half, there's going to be an asymptote here too. I feel like this tick is sort of like off. It should be like over here. Yeah, oof, that's ugly. Sorry, it's kind of off screen. That's what we're working with. Okay, and I should mark off my midline as well, which is -2, but there's like, again, the distance between the midline and the vertices is just a distance of 1/4, so I want to be mindful of that and kind of really scale this y-axis out. So I'll maybe do it by like 1/2. Here's 1/2, -1, -1.5, -2. -2.5 as well. There we go. Okie dokie. So now I just need to figure out the orientation of the U's. Is there going to be an upward facing U in this slice? Is it a downward facing U? I don't know, personally. So what I do is I just test points. Right in the middle of this, 0, and this is pi/2 right here. The midpoint between 0 and pi/2 is pi/4. I know that there will be a vertex at x equals pi/4. So when x is equal to pi/4, y is equal to, let's see, -1/4 times the secant of, what happens in here? 2 times pi/4 is pi/2. Pi/2 plus pi/2 is pi. So -1/4 times, so the secant of pi, cosine of pi is -1. So secant of pi is -1. Minus 2, this becomes -1/4, oops, sorry, +1/4 plus 2. Let me see if I can erase that a little bit better. There we go. Oh, jeez, not +2. I mean, technically, plus -2. So 1/4 minus 2 is -1.75, or -1 3/4. Which means that at x equals pi/4, there's a vertex at -1.75. So right here. This is above the midline. So it's going to be an upwards facing U. The very last thing that I would do in here, though, is because this has a is equal to 1/4, if the absolute value of a, or I guess just a in general, is between, absolute value of a, because we don't want a to be 0. That kind of ruins the whole point of it being trig function. So if the absolute value of a is between 0 and 1, it's kind of like a squashing factor. So what that means is that as the function passes through the vertex, it kind of like flattens out like this, and then it goes off to infinity as best as possible. I'm not an artist, so okie dokie. Then I know that there will be a downward facing U here, and the downward facing U has a vertex of -2 minus 1/4, or -2.25, so it's going to be right here. Same idea, it's going to be nice and fat right here near the vertex. Like that. It moves through the vertex slowly. So something like that. So there's one period of it. Again, you can just keep repeating if you need to graph 2 periods or however many periods you've got. Okie dokie, so that is graphing cosecant and secant given a equation.